Good morning, all. This is Harishwar Reddy, working as an assistant professor in mathematics at TCAS Engineering College. Today, I'm going to explain how to convert a Bernoulli equation into linear form. So, before to start that, I will explain what is linear equation, what is solution of that equation. Then we convert the Bernoulli equation into linear differential equation. So, the linear differential equation is in the form of dy by dx plus py equal to t. So this is called linear differential equation in y, and here x is independent variable, where p and q are q are functions of x, functions of. So this is linear differential equation in y with respect to x. The general solution of this equation is the general solution. The general solution is y into integrating factor is equal to q into integrating factor dx. So this is general solution of this equation. This is linear differential equation in y, and this is general solution of this equation. Now I'm going to convert Bernoulli's equation into linear form. Generally, the Bernoulli's equation, Bernoulli's dy by dx plus p into y q into y or l. This is called Bernoulli's linear differential equation in y. We have to convert this Bernoulli's equation into the linear form. So before going to convert this equation into linear differential equation, here in right hand side y for n is, it may be n is 1, either 1 or n not equals to 1. If it is n is equals to 1, how to convert, and n is not equals to 1, how to convert into linear form. Suppose case 1. If n is equals to 1, if n is equal to 1, so then the Bernoulli's equation, it will be in the form of dy by dx plus dy equals to 2 into y power 1. Now the equation becomes dy by dx plus py minus is equals to dy by dx plus p minus q y is equals to 0. Now separating the variables, dy by dx equals to minus of p minus q y. When we are separating the variables, we get dy by y minus p minus q. Now integrate both sides, dy by y minus p minus q, So its integration is ln y. We don't know what is p and q. P and q are functions of x, so that is why we leave it as it is. Integration of p minus q plus. This is a general solution of the Bernoulli's equation when if n is equals to. So this is case 1. Now come to the case 2. Case 2. If n is not equals to 1, n is not equals to 1 means either it may be negative real number or positive real number, except n is not equals to 1. So how to convert this equation, and in this case, the Bernoulli equation into the form of linear form? So firstly, I'm dividing equation with y power m. What we're getting here? Y power minus m dy by dx plus p into y power minus m is equals to y power minus n dy by dx plus p into y power 1 minus n is equals to. So I'm giving equation number. Now I'm assuming I'm taking here y power 1 minus n is equals to, while to convert to the linear form, I'm taking y power 1 minus n is equals to, differentiating this one with respect to x, both sides, we get 1 minus n dy by 1 minus n y power 1 minus n minus 1 dy by dx is equals to dy by y power minus 1 plus 1 is cancelled. Y power minus n dy by dx equals to, here it is multiplying. If it goes to that side, it will divide 1 by 1 minus n by. Now I'm substituting these two in equation number 2. We get in place of this, I'm substituting 1 by 1 minus n dy by dx plus p into u is equals to. So the linear differential equation does not contain the coefficient any real number or any real number, any function. So to free from that, I am multiplying entire the equation with 1 minus n. We get du by dx plus 1 minus n p into u 1 minus n. Now, so this is linear or not. So once we check it, du by dx 1 minus n is constant. So p is the function of x and u is dependent variable. 1 minus n is a constant. Now when we are comparing this equation, linear form, dy by dx plus dy is equals to 2. So therefore, the given Bernoulli equation converted into linear form, and it is linear in u, and p and q are functions of x. So the general solution of this equation, is u into integrative factor is equals to 1 minus n q into integrative factor. So this is the way to convert the Bernoulli equation into the linear equation, and in this case, the general solution is u into integrative factor is equals to 1 minus n q integrative factor dx. After integration, so substitute in place of u y power 1 minus n. This is the general solution of the given Bernoulli equation. Now, we will see one problem. Solve dy by dx plus y is equal to y power 3. The given equation is The given equation is Bernoulli's equation. It is not linear equation. Why means in right hand side, in linear equation in right hand side, it does not contain any y term, but this equation contains y terms. So therefore, this is a given. This is the Bernoulli's equation. So we convert this equation into linear equation and find out the integrity factor. Then we can write the general solution of the given for this equation. So we have followed the procedure of converting Bernoulli's equation into linear equation. Now, given that dy by dx plus y is equals to y power 6. The first step is divide this equation with the y power 6. We get y power minus 6 dy by dx plus y into y power 6. Sorry, y power minus 6 is equals to y power minus 6 dy by dx plus y power minus 1 is equals to 1. Now I'm taking y power minus 5 is equals to u. Differentiating this one with respect to x, both sides. Minus 5 y power minus 5 minus 1 dy by dx equals to y. Y power minus 5 minus 1 is minus 6 dy by dx minus 1 by 5 dy by dx. Now I'm substituting these two. This my y power minus 6 dy by dx is equals to minus 1 by 5 du by dx, and y power minus 5 is equals to u. In equation number star, we get y power minus 6 dy by dx equals to, we can write 1 minus 1 by 5 du by dx. I'm writing here minus 1 by 5 by dx plus, in place of y power minus 5, I'm writing u equals to 1. So the linear equation, the coefficient of du by dx does not contain any term. So that is why I'm removing this term. To remove that, I multiply with minus 5. We get du by dx minus 5 equals to minus 1. Now, so this equation is the form of linear equation in u with respect to x. So we have to find out the integrating factor. The integrating factor is e power p dx is equals to integrating factor of e power. What is p here? P is minus 5. Minus 5 equals to e power minus 5. Integration of 1 is x minus 5x minus 5x minus 5x. So this is integrating factor. Now, the general solution of this equation is u into integrating factor is e power minus 5x equals to q. What is q here? 1. Sorry, minus 5 e power minus 5 dx. U into e power minus 5x minus 5. The integration of e power minus 5x. So that integration of e power ax dx, e power ax by e power minus 5 by minus 5. Minus 5 minus 5 is cancelled. Now, what is u here? U is y power minus 5. I'm substituting now. Y power minus 5. E power minus 5x equal to e power minus 5x plus c. When I'm taking e power minus 5x is common, e power minus 5x is common. 1 plus c e power 5x. So e power minus 5x, e power minus 5x cancel. Y power minus 5x, sorry, not 5x, y power minus 5 is equals to 1 plus e power 5x. So 1 by y power 5 is equals to 1 plus 4 5x. 1 is equals to y power 5 plus c e power 5x y power 5. So this is our general solution of the given Bernoulli's equation. Similarly, so far we have seen Bernoulli's equation in y. Similarly, we can see Bernoulli's equation in x. That is in the form of dx by dy plus px equals to x into x power n. Here, this is in Bernoulli's equation in x, where p and q are functions of y. So before to convert this Bernoulli's equation in x into the linear equation. So the linear equation in x, we see that one dx by dy plus px equals to here p and q are functions of y. So how we have converted the Bernoulli's equation in y into the linear equation in y. Similarly, same procedure we have to follow the Bernoulli's equation in x to convert into the linear equation in x. We see one problem in this case. Dx by dy plus x power x cube. So this is Bernoulli's equation in x. So now we have to find the solution Bernoulli's equation in x. Given that dy by dx plus x cube. So converting this Bernoulli's equation into linear equation, divide entirely with x cube. We get x4 minus 3 dx by dy plus x into x4 minus 3 is equals to x4 minus 3 dx by dy x4 minus 2 is equals to 1. Now I'm taking x4 minus 2 is equal to u. Differentiating with respect to y, we get minus 2x minus 2 minus 1 x by dy is equals to by x4 minus 3 x by dy equals to minus 1 by 2 du by dy. I am substituting these two in equation number. We get in place of this we can substitute minus 1 by 2 by dy plus x4 minus 2 is u equals to 1. So if we minus 1 by 2 the coefficient of du by dy, I multiply with minus 2, enter the equation, we get du by dy plus minus 2 into u equals to minus 2. So when we are comparing this equation with the linear equation, this is a linear equation in the form linear equation in u. The integrity factor is e power minus 2 e power minus 2y. Integrity factor is e power minus 2. The general solution of this equation is u into integrity factor equals to q. What is q of minus 2 into integrity factor? Q is what we have taken u x power minus 2. X power minus 2 integrity factor is e power minus 2y equals to integrity factor is e power minus 2y dy. X power minus 2 e power minus 2y is equals to minus 2 e power minus 2y dy. X power minus 2 e power minus 2y minus 2. The integration of e power minus 2y is e power minus 2y by minus 2. Let's see. Minus 2 gets cancelled. X power minus 2 e power minus 2y over minus 2y. When I'm taking e power minus 2y is common, 1 plus over e power minus 2y, e power minus 2y is cancelled. So 1 by x square is equals to 1 plus what? X square is equals to 1 by 1 plus 4 to 1. We can write x square plus x square into 1 plus c power 2y is equals to 1. So this is our general solution for the given Bernoulli equation in x. The general solution is x square plus x square times of 1 plus c power 2y is equals to 1. Now we'll discuss about the higher order linear differential equations. Higher order linear differential higher order linear differential equations. The general form of the higher order linear differential equations is a naught nth derivative of y by plus a1 from dn minus 1 dy by dx plus dn y is equals to. The general form of the higher order linear differential equations is this one here. A0, A1, and so on, AN minus 1, AN are either constants or coefficient or functions of x, and if q of x is either it is 0 or function of x. Suppose if q of x is 0, suppose q of x is 0, it is higher order linear differential equations and homogeneous. If it is not equals to 0, higher order linear differential equations, it is non-homo and it is non-homogeneous differential equations. Okay. Suppose and there are different methods are there to solve this higher order linear differential equations. When suppose the constants are coefficients and right hand side, what we have q of x is if it is 0, a naught by x plus a1 n minus 1 to derivative y plus and so on a n minus 1 by dx plus a is equals to 0. So this is higher order linear differential equations and homogeneous. Why it is homogeneous? Q of x is here, Q of x is, and the order is n, and a naught should be not equal to 0. If a naught is 0, order does not exist. So that is why a naught should be not equal to 0 and order is n. So in this case, so this is higher order linear differential equations with constant coefficients. Here a naught, a1, a2 and so on, an minus 1, then r real constants. Real constant and a not equal 0 and q of x is. So this equation is called higher order linear differential equations and it is homogeneous. So in this case, how to find the solution for this equation? So before finding the higher order linear differential equation solution, first we have to convert this equation in operator form. Then we write the auxiliary equation. So finding the when we are converting into the auxiliary equation, we get polynomial equation. For the polynomial, we have to find the roots. We can find the roots. When we are getting the roots, we have to write the solution for this equation. Now we see what is operator form. The differential operator is d by dx. Where we have d by dx, of d by dx, we can write capital D. So when we are converting into the operator form, now I'm writing a naught d power n. This is a1 d power n minus 1 plus and so on d plus 1 sorry a n minus 1 d plus a n y is equals to. So this is operator form, or we can simply write f of dy is equals to. So this is operator form of the given higher order linear differential equations. Now, after writing operator form, we can write auxiliary equation. Auxiliary equation. The auxiliary equation is f of n is equal to 0. In place of d, you can write m. We get an a naught m power n, a1 m power n minus 1 plus and so on. N minus 1 m plus an equals to. So this is a polynomial equation of degree n. So we get how many roots we get here? M roots. N roots. The degree is n. The degree is n. We get for the equation n roots. What the roots are m is equals to m1, m2, and so on. And how many roots we get here? For this is the polynomial equation of degrees and we get n roots. So the solution of this equation is depends on the nature of the roots. If the roots are real, we write the general solution, and the roots are real and distinct, we can write some cases. We have follow some cases. Okay. So we can start it here.